When I think about my childhood and I think about the dreams that I had, a lot of them come down to pictures like this. This is me busting out a really bad dance move on the ceiling of a 727. And I was there with a group of students and faculty that I had arranged at MIT. We were the first charter flight for Zero G's research program. We were on that aircraft trying to figure out all sorts of things, from how skin-tight spacesuits work, to nanosat microthrusters, to the way that proteins and foams interact in microgravity. Turns out that that one is really interesting if you ever want to pour a beer on your future space station. But what we were seeing here is that if you talk about, sort of step back and think about what's going on at Satellite this week, most of this conference is about space as a place we go to, a place we look from. For me, the thing that excites me most and what I'm going to sort of geek out about this morning is space as a tool. Space is a different way of thinking about the world. And I think one of the easiest ways to see this, and Liz, I'm just going to point at you for the slides, is taking a look at something that's very physical. So here you see flames. Flames on Earth have this little shape that's kind of like a teardrop. It's the shape that my 7-year-old draws on birthday cards. And that happens because of convection. Because as the cold oxygen comes into the base of the flame and combustion happens, hot products of combustion rise up and they pull that flame up. In microgravity, that doesn't happen because hot things, less dense things, don't rise. We don't have to worry about that on space. But what we instead get, it's okay, go ahead, Liz, is we get these cool spherical flames. What you're seeing here is a picture from Foreman Williams' flex experiments on the combustion rack on Space Station. And you see that flame that's a perfect sphere. That's not only beautiful, it's also really interesting because it turns out if you're trying to model what's happening in combustion, it's way easier to model the world as a sphere than to model it as this dancing flame. So we can learn a lot about the basics of combustion. But what's even more wild is what's happening right now that you can't see. And that is that they actually kept the cameras running on the flex experiments and found something weird. They found that after that 3,000-degree ball of flame went out, what they ended up with was this 1,000-degree ball of cool flame. And then you start to see this evaporation of the heptane and the products of combustion, and we're actually seeing burning in a way that we can't see on the ground. It turns out that these cool flames are present in engines. It's how you get ignition in an engine, but they're gone like that in 1G. In microgravity, we can study how they evolve and change. We can model them more clearly because they're this simple sphere. So by looking at the things that were unexpected on Space Station, we're learning a lot about how we make engines more efficient here on Earth. Moving from flames to fluids, these are a couple of videos from Don Pettit's Saturday Morning Science series on the ISS. Really cool stuff. This is a very simple Alka-Seltzer tablet into a bubble of water. But light things don't rise, heavy things don't sink. So instead of getting a layer of bubbles and a layer of liquids, what you get is this sort of conglomeration of fluid and air. And it shoots off these gas jets from time to time as the surface tension breaks. But there are times in space where you really want to know where your liquid is and where your air is. If you're trying to measure the amount of fluid in your fuel tank, if you're trying to manage the waste management system on your spacecraft. In which case, if you can get that second video up, Liz, you really want to be able to separate out your liquids from your air. So one of the things that's been really interesting to see in the fluids community is they've been learning how to manage fluid with geometry. And this is, it's actually the cover torn off of a protocol binder from the space station, and Don has shaped it into a teardrop. And down at that corner, you get a wetting angle that is perfect for capillary action. Now this is another one of those surface tension-driven phenomenon, just kind of like what we're seeing in the bubble. But what it does is it wicks down all the fluid to that corner. And you can then use that as a means of transporting liquid around your spacecraft, around your systems. This is super handy, again, for things that are happening in space, but it also turns out to have real applications here on Earth. This is the same thing that at the nanoscale is happening in microfluidics. So if you're making medical diagnostic chips, if you're making any sort of microfluidic device, this is the same thing that we're using this science to make life better here on the ground. It also turns out that it is the perfect way to make a temitas for sipping espresso in the cupola. So if anyone is ever thinking about their morning coffee in the best view possible in the universe, I think this might be it. Moving from fluids over to other systems, fluid and air, to mixed fluids and materials. Here you see Richard Garriott with two immiscible fluids. Think oil and water. And when you shake up those fluids in 0G, again, density doesn't mean the same thing when you're in a microgravity environment. So we don't get layering. We don't get that separation. So think about what that would look like if you were in a colloid, if you're trying to make a new material, if you're trying to make an alloy that on the ground would separate out into layers. But in space, you can get the perfect material that you're looking for. And it turns out that this is particularly interesting right now if you're looking at glass. I'll leave some of the real fun stuff to Justin Kugler later in the day at Made in Space. But here you see some really interesting work from Dennis Tucker in the 1990s, first on sounding rockets, then on parabolic flights. And this is a fiber optic cable. This is a piece of glass that has been stretched out until you can transmit light through it. When you do that in 1G, there are denser molecules within that glass that want to crystallize out, and they make these little dots. And every one of those little dots reduces the transmission of your signal through your fiber. But when you do the same thing in 0G, you don't get that crystallization. You don't get that falling out in solution because you don't have the same impacts of gravity on your system. And that ends up giving you these perfectly clear glass structures that make from medical lasers, higher bandwidth fiber optic communications. All the power of microgravity there. Now there's a number of different ways you can get to micro-G. When I was working at MIT, people used to ask where the room is where they have that G switch, so you can just turn it off. I wish we could do that. Right now, we're stuck with drop towers, parabolic flights, sounding rockets, suborbital rockets, International Space Station. This one happens to be my favorite, New Shepard. I spend a lot of my time working with our customers that are trying to do science experiments on board our rockets. If I can get that next slide, Liz. This is from our mission in December, our first commercial flight. We had a number of payloads. I just want to tell you about two of them. On the left, you see Professor Stephen Collicott from Purdue University. Now, Stephen is a fluid physicist, and he was working on this experiment with a small business here in Richmond, Virginia, that makes medical devices. And they started to ask the question of how would you treat a collapsed lung in an astronaut on space station? At the end of the day, this is an air and fluids problem. How do you separate the air in the lung from the blood that you're dealing with? It's a really interesting question that gets solved really nicely and elegantly with that same teardrop-shaped geometry that we saw in Don Pettit's cup earlier. So they were running some protocol trials on this, seeing really fantastic separation. And on the right is my favorite experiment that we've flown on New Shepard to date. These are, oh, don't steal my thunder there. These are our second graders from Cumberland Elementary that were passionate about fireflies. Now, these are little beetles that light up at night. If you're from the South, you've seen them your whole childhood. But they started to ask the question of, can fireflies light up in 0G? And rather than giving them the answer, the parents, the teachers, and the neighbors came together. They had a pancake breakfast and a PTA fundraiser, and they started their own space program at their school. We're in the era that's possible now. And they flew this experiment, and it turns out that luciferin and luciferase can absolutely glow in 0G. Fireflies are fine when we find them as our neighbors. But even more fun was that they took these results down to the Indiana State House. And just a couple of weeks ago, I got an email just cheering that the Say's firefly is now the state insect of Indiana, thanks in part to the work that the students have been doing. So when I think about this opportunity that we can do fundamental science in combustion, that we can develop technologies and test them out in ways that give us new insights, new systems for the future, and we can inspire the next generation. It's another one of those things that just makes me want to dance on the ceiling. Thank you very much.